and it was kind of cool.
So early?
What happened? It's kind of cool. And you could actually, if you wanted to calculate how much money your money made in, like a second of the day. It wouldn't be a lot, right? But you could calculate that. So you could get it down to an instantaneous rate. At any one time, this is what you're earning. And if you add up how much time elapses, that gives you the total growth for that time period. So what we're talking about is calculating something called R, which is the per capita instantaneous growth rate. The rate any one individual contributes to a population at any one time. And obviously this isn't a real number in terms of you go out and measure this. This is something you derive by averaging things you measure over longer intervals. And you sort of average it out to an individual for an instant time. And there's different ways of getting at this, but the nice thing about this is if we can calculate this, all we have to do then is estimate what the total number of individuals are and the time frame we are going to allow to elapse, and that will tell us how much that population will grow in that time. It's basically a slope that you apply to a line on a graph to tell you how much that value is going to increase over time. So, sometimes it's known as the instantaneous growth rate. Just add water. And to get at it, you have to understand a few things about the way populations grow. And we're also going to show how you can relate this rate to the rate we've already talked about, R sub 0, big R sub 0, and other rates that you can derive. So, when we think about population growth, sometimes it's nice to think in a utopian environment, in an ideal world, in the perfect circumstance. Every species has this potential hypothetical value called the intrinsic rate of increase. And that is, if nothing limited population growth other than the ability of organisms to physically crank out offspring, right? Which is a biologically engineered constraint. You think of any organism, humans are constrained by how many fetuses can fit in and be carried to term in the womb, right? Other organisms are limited by how many eggs they can produce and carry or lay. So if you thought about what are the actual, if there were no external limitations in terms of not enough food or access to mates, if everything was optimum, then populations each have their own inherent maximum rate where they can grow. And you could improve conditions even more, and you wouldn't get more growth because they basically maxed out. It's kind of like everyone has a different car, or a lot of you have cars. And my guess is if we were to do a survey of all the different kinds of cars you had, you'd have quite a spread. Some of you would be economically more certain of cars. And some of you would be potentially compensating for something and having 8% cars. And each one of those has a maximum speed that can be achieved. And you can put it on, the Autobahn without a car in sight, and you can't go faster than that maximum speed, even if conditions could allow you to go faster, because you've reached the absolute ceiling of your capabilities. But as we all know, from the reality of driving, we very infrequently drive at that maximum capable speed, right? Particularly at 5 o'clock when the highway runs going south. So, we can think of R as a rate as being anything. Population can increase, decrease, or stay constant. But, under the right conditions, there is this theoretical value, R max, which is the intrinsic rate of increase, the maximum rate that a population can grow. It's the highest possible R that is ever going to be achieved for a species. And to get that, obviously, a lot of things would have to be true. There couldn't be any kind of resource limitation, because if there was resource limitation, some organisms would not be producing as much as they could, or at all. There has to be complete access and availability of mates to reproduce with. There has to be physical space and all the other resources required to have offspring, and in some cases, if they're post-parental care, raise them. So there are a lot of constraints on this. Okay? And so these are biological constraints. You can think of that as an engineering design, the design limitations of a particular species. So you might imagine that different species have different Rmaxes, right? Humans would have one Rmax. Mice would have a very different Rmax, right? So what do you think would be higher, the Rmax of humans or mice? Mice, okay? Argentine ants have an insanely high Rmax because they go and produce a million eggs, and next thing you know, you have a million more ants coming in your kitchen looking for water and food. So different species have different Rmaxes, and that's a function of their individual biology. Some are designed to crank out offspring more quickly than others. So if we were to plot a bunch of different species in their Rmax, they would look different, but there would be one thing that would be the same about all these plots. So I'm going to show you a bunch of plots of different species, of hypothetical Rmaxes for a bunch of different species. And you'll instantly see what's different about them, but I want someone to tell me what's the same about all of these plots. So there's a species with a very low Rmax. There's a species with a low Rmax, a moderate to high Rmax. So you can clearly see how they're different, right? They increase at different rates. But what's the same about all four of these curves? Sorry? They start at 0? Well, that's technically true, but not what I was getting at. Yeah. They all are what? They all increase. That's true, but I'm looking for something a little bit more. Huh? That's right. Ding, 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 ding. Right. Winner, winner, chicken dinner. Okay. These are all examples of some variation of the formula y equals x squared. Right? They're parabolas. Right? Parabolic growth. So it's exponential growth. And that is what maximum growth rates of populations take on. That's what we call exponential type growth. In a perfect world without resource limitation, the growth rate is exponential and infinite. There's no limit to how high the population can go. Of course, that's never seen anywhere in reality, but that's the starting point. That's the conceptual starting point to understand what is the absolute maximum possibility of a population's growth. Okay? And how do we determine that value for a particular species? So, another thing we have to understand is populations manifest their growth in different ways. Populations reveal their growth to us observing them in different ways. Some populations grow discretely, and some grow continuously. What does that mean, discretely? They get in all their growth out of sight, very discreet. No, that's not how that works. The discrete growth means it occurs in very specific intervals. So there are periods where there appears to be no growth, and then there's a big jump in numbers, and then there's a period of no growth and another jump. So the growth occurs in discrete intervals. What type of breeding strategy do you think would be demonstrated by an organism, a population that grows discretely? Seasonal, exactly. All the growth occurs at a particular time of year, and there's no reproduction in between breeding seasons. So all the growth of the population occurs after a breeding season. Versus continuous growth, where that's more in terms of aseasonal populations grow continuously. They're always reproducing and adding individuals to the population. So populations with distinct breeding seasons demonstrate this classic pattern called discrete growth. Where you see all the growth occur following the breeding season and no growth occurring until the following breeding season. Whereas populations that produce year-round demonstrate continuous growth. So if we were to plot human population growth, right, we would distribute, trying to find the word, we would demonstrate, what type of growth, discrete or continuous. Thinking back to our little hand-raising exercise on Wednesday. Continuous. That's right. Continuous growth. Whereas elephant seal population, which reproduces at a certain time of year, would have discrete growth. All right. So what does this look like? Well, here are two types of growth: discrete growth versus continuous growth. On the y-axis is number. On the x-axis is time. I really should label them. I should admonish myself for not labeling my axes. If I'm going to take points off on your exams for doing that, I should penalize myself similarly. So, consider myself point protected in the great cosmic scorecard. So, you see the pattern here. All the growth occurs at very discrete intervals in discrete growth. And you know when the breeding season is, it's the period of time immediately preceding the big jump in value. And then there are periods of time in which you have no growth, right? As opposed to the continuous growth curve where the increase is temporary. But here's the interesting little cruel reality. Those two are actually basically the same thing. Because if you connected the corners on the first, you would get continuous growth. So we can derive continuous growth rates using discretely growing populations. I just taking 2 points on a line and doing some simple math. Right? And that's exactly how population biologists typically do this. They calculate a discrete growth rate and then use a simple mathematical relationship which relates to this exponential curve to calculate what the instantaneous growth rate is. And that's basically how the bank calculates your interest. It doesn't calculate it once a year, it calculates it daily or weekly or whatever, but that rate it calculates comes from the annual interest rate, which then they derive the daily interest rate. So it's no different than the kinds of calculations your bank used to make when it gave you interest on your money. Trying to figure out ways to charge you more and more fees for the privilege of having them hold your money. All right, so let's start with discrete growth. Here's how we calculate the growth rate for discrete growth. Now we can describe stuff, we can determine, count, empirically derive some value, n sub 0, which is the population size at time 0. Now, and come back at a year later, let's say, and the best time to do this would be either before or after the breeding season, but you always want to do the next measurement at the same time of year. So you had only one breeding season that's even out, right? If it's a seasonal breeder. And so N1 would be the population size at some time later, let's say a year later, year 1. So now we have a ratio. We can calculate a growth rate from these two values, can't we? So it's simple, the discrete growth rate, which is always symbolized by lambda, this letter lambda. So just out of curiosity, how many of you belong to a fraternity or sorority with the letter lambda in it? Okay. Nobody. That's below the end. Okay. Lambda is usually a popular one, isn't it? Right there with Delta. The Delta fraternity. You know that movie Animal House? No. I would have liked it. All right. So we can do some simple math and rearrange that expression. And we can say if we can determine lambda empirically by doing this calculation, right? Then we can do some simple algebra to say, well, we can predict or we can calculate the population at some time by multiplying the existing populations by the growth rate, lambda. Right? That's just simple algebra. And we can generalize this expression to use this expression to predict the growth anytime in the future by saying that the population size at some time in the future, n sub t is, let's say, 4, it would be n sub 4 equals n sub naught times lambda to the 4th. Right? It's a simple generalized mathematical relationship. It's very straightforward. So this is how people determine growth rate using discretely growing populations. Or even if it's not discretely, you measure it discretely. You just come back at the same time each year and measure the population size and calculate the growth rate. Now, did everyone get that? Yes? Now, there's going to be a summary slide on the webpage with all the formulas you need to know, all the expressions you need to know. If you missed them in the lecture, you'll get another bite at that apple on the webpage. And there's going to be some problems that you can do on the webpage too. All right. Now, what about continuous growth? Well, if you think of lambda as a rate, it's like an annual interest rate. It's the amount of growth you achieve in a year, right? So we can basically come up with a relationship to tell us, mathematical relationship, to tell us what the relationship is from the yearly rate to the instantaneous rate. So that's the growth rate over a discrete period of time. And this little r we're trying to calculate is this per capita growth rate. And that's what the rate is at any instant. So basically, you remember those plots of those parabolas? Lambda would be the rate between two discrete time periods along that parabola. But r is the rate at any particular point along that parabola. So you've got to use some mathematical knowledge to come up with a relationship between r and lambda. And it turns out it's a pretty simple relationship. It's almost natural in nature. Right? Natural. Which is somewhat redundant, right? Okay. But what is the relationship between lambda and r? Well, it's pretty simple. Anyone want to guess what it is? Linear. Well, lambda equals e to the r. That's where the natural comes in, right? That's the natural antilog, right? So the natural log of e is what? 1. Okay. So if you take e to the r, that equals lambda. And that has to do with this exponential function, right? So if I can calculate lambda, I can just do a simple equation, take the log, the natural log of lambda, and that gives me what? R. So it's a very simple mathematical relationship. And so that's how R is determined. You never actually empirically calculate R because you can't calculate an instantaneous growth rate. You go there and get your stopwatch and go, now! Okay? Wait, it didn't grow, right? So that doesn't work. It's more of a theoretical concept that you can apply mathematically to predict population. But you can measure the discrete growth rate. That's a very doable thing. And, depending on how long the breeding seasons are, it might only be a year. Okay, so you come back a year and you measure the growth rate. So now that we know these relationships, we can sort of interchange them and use them to predict or measure population growth. Now, let's go back to that R sub 0. Turns out that R sub 0 is related to R as well. Now, R sub 0 was the growth rate over a what? The individual growth rate over a generation, right? So we're going to have to standardize whatever it is to a generation to compare it to R. So R sub 0 is the generational growth rate, which we can calculate using life tables. And R is the per capita or instantaneous growth rate. So what's the relationship between the two? Very simple. R is the natural log of R sub 0 divided by G. G is the generation time. Now, trick question, not a trick question. What's R sub 0 divided by G?
What's G? G is generation.
Well, what's the log? What do you take the log natural of to get R?
0. 1. R. E.
Previous slide. Lambda, right?
Oh.
R sub 0 divided by G is just lambda. G is the number of years an animal produces. You divide the total of years, you get the production for 1 year. That's the discrete growth rate, lambda, right? So basically what that's saying is take a log natural of lambda and you get r. But lambda is r sub 0, the generational growth time, divided by the total number of years. Okay? So they're all related. So the point is you can determine growth rates a number of different ways. You can do lambda, you can do r sub 0, and once you have that, you can then adjust and convert your rate to suit which form of growth rate you want to use in your calculations. You just basically convert and go back and forth. We're going to show some examples of using lambda and r to do that. Okay. So this is just, don't write this down. This is the slide I'm going to post on the webpage. It summarizes everything we've talked about in terms of growth. So in terms of life tables, you have to know what alpha x refers to, n sub x refers to, and this value you calculate the sum of alpha x, n sub x, which is r sub 0, or net reproductive rate, generational growth rate. Yes? Generation time. No, how many years an organism produces? Then we talked about determining lambda, the finite rate of increase. The specific way of doing it, an example, n sub 1 divided by n sub naught equals lambda. We can take that relationship and make a generalized expression, n sub t equals n sub naught times lambda to the t. So lambda is the finite rate of increase. And then r is the per capita rate of increase, and there's this relationship between lambda and r. So if we substitute e to the r instead of lambda, then we can take this expression, n sub t equals n sub naught times lambda to t, and now n sub t equals n sub naught times e to the r t. Because when you do exponents, you add them together. So that's a simple expression that tells you the relationship of all of these different values, how we calculate population. So this page is going to be, it already is, in fact, posted on the website. All right. Let's use this practically. And talk about some questions you might do trying to measure growth rates, reduce growth rates, or other particular questions you might have using a population of endangered grouping frameworks.
Trees.
Okay. Interesting bird, endangered bird, migratory bird, flies from the north of the United States and Canada to southeast of the United States for wintering grounds. And let's take an example here. So let's say there's 20 cranes alive in 1949. And in 2004, a population census revealed there were 425. So I want you to calculate the instantaneous growth rate that population demonstrated for that particular idea. Right? So this is like a math problem, right? What do they always tell you to do in a math problem?
Identify your...
Write down what you know and write down what you're trying to find out. And try and just, like a jigsaw puzzle, rearrange what you know to make one thing you need to find out. A expression that you can solve. Right? Okay? Either love these or hate them. Right? Okay. So what do we know? We know a lot from that 1%. We know what n sub naught was. 20. We know what n sub t is. 125. And we know what t is. 2004 minus 1941. Which is 63. And we know the relationship between all those things. N sub t equals n sub naught times d dt. So we're going to plug in all our values and solve for r. Okay? That's the fun part. Now, by the way, if you're scribbling, stop. Every one of these is posted on the webpage. And a couple of others that we're not going to go through a lecture, that you can try and do yourself and see the answer. Okay? So, sit back, relax, enjoy the flow. All right, so, unless you want to try and beat me to the question. Okay, so here it is. N sub t, 425, equals n sub naught, 20, times e to the rt. So what's the first thing we're going to do?
Take the log of both sides.
Divide both sides by
20.
20. All right? Now what do we do?
Take
Take the natural log of both sides. Right? Now what do we do?
Divide by
both sides
63.
by 63. There's our r. And that is a complete answer. I don't want to see a number. I don't care about a number. Couldn't care less what the actual number is. Probably completely, in reality, nowhere near the truth. Okay? I want to know, do you understand the process by which we get to this number? So this would receive 100% full credit, but the great thing about this process on a test question is I can chart your line of thinking and reward you for those parts that you get right. You can get partial credit for a wrong answer using this approach. If you just give me a number and it's wrong, you'll get no credit. If it's right, you might get 1% credit. So we haven't told you know anything. You just need credit, you get guessing. Now, someone's already gone out there and calculated. I guarantee you. Who has? Come on. Fess up. All right, nobody?
Nope. No one seems interested.
Well, it's 0.049. That's what the R turns out to be. You actually do the math. So let's now tweak a little bit differently, a different scenario. If R is 0.0046, which is reasonable, we just calculated an R of 0.049, and we assume that rate will not change for the foreseeable future, and we go out and we measure a flock and it has 189 individuals, how long is it going to take for that flock to double? So now we're going to calculate the time value. And this is a realistic question. You might be a conservation manager tasked with recovering the current population to twice its size. And you've been asked to submit a budget. And in that budget is your annual salary. You want to make damn sure there's enough money in there so you'll be able to pull a paycheck for all the years you're going to be working on this project. Okay? So there's nothing high-minded about this. It's purely selfish, right? You're interested, in maximizing your fitness, financial fitness. So you want to make sure that you have enough money in your budget to allow you to recover this population size. So what do we know? We know what N sub naught is. We know what N sub T is. We don't know. We can calculate what N sub T is because we double N sub naught. We know what R is, and we know the relationships. Now we do exactly the same thing, but now we plug in the numbers and solve for T. So we do it basically the same way. N sub T equals N sub naught on DDRT. We divide both sides by N sub naught. We take the natural log of both sides. We divide both sides by R. And do this math and wind up with 15.06 years. So about 15 years. So you've got gainful employment for the next 15 years. That. Right? Now you might fudge the numbers and come up with a lower R and get yourself a little bit more job security. All right. So there are a couple of more problems in the web page. One that's a little bit more tricky to get at. But the answers are on the following pages. So if you want to go through and try and do those problems yourself. But if you can understand the logic behind doing these problems and the values that you're plugging in to do that, how you derive those values, you'll be fine with any equation I might ask. And again, I don't want a number. I want the simplest expression where what I am asking the value is R or T and some expression of functions and numbers on the other side telling you what you have to do to calculate this. But don't do the calculation. You won't be allowed to have a calculator anyway. Not too many of you can do natural logs in your head. All right. Now, that's all and well in a utopian world without resource limitations. So all these problems we talked about, addition, population, where the growth is exponential and never slows. And sometimes you actually see this kind of growth. It's very typical in populations that were hunted to near extinction and then are completely protected. And at first they grow very rapidly because there's all this unused resource and space that they can have access to. And they're not competing with high numbers of individuals to acquire resources. So an example are northern elephants here, which were almost hunted to extinction in the early 1900s. And one small remnant population survived in Guadalupe Island, which is off of Baja, California. And then the Marine Mammal Protection Act protected them, and they have exploded in numbers since then. And we showed you an example of that when we talked about that as an example of genetic bottling, which means totally instructive, genetic bottling. So, that's exponential growth. But the reality is, if this goes on much longer, it ain't going to keep going that way, right? So here's an example of that same health insurer population. Here's another example of some reindeer on St. Matthew Island, where all the predators were removed and hunting was prohibited. And sure, the deer grew really fast. And then all of a sudden, bam, they crashed. Why? Because they grew beyond the resources that could sustain them. And then that was hit by the perfect storm of a really harsh winter. And there was just too many mouths to feed, not enough food to feed, and then there was massive dying. Right? This has happened in a lot of examples. The classic one in the Scott ecology courses is the population of deer on a place called the Kaibab Plateau, where the population was protected from hunting, all predators removed, it exploded, and then crashed. So that's more like the case. And why did it crash? What's happening as the population gets bigger and bigger and bigger and bigger? What reality is befalling these individuals? What's getting more and more? Think back to our buddy Clinton Malthus. Resources are becoming increasingly limited. And there's increasing what for those resources?
Competition.
Survival. Population grows too quickly, right? Then all the resources will be drained, and there's going to have to be a big die-off. Yes?
So if there wasn't that peak, that very big peak, would it drop all the way down? So let's say it peaked midway, and then the cold winter came.
Yeah.
Would it have crashed to that same point?
Probably not as much.
Okay.
Yeah, but certainly it would have crashed. I mean, the environment factors. So the higher the population comes, the more intense competition gets for resources. So there is a relationship between certain factors and the density of the population, right? There's a relationship between them. So in reality, populations in nature don't demonstrate this kind of growth because this resource limitation gets incorporated into the growth of the population. It kind of puts the dampers on population growth. It retards it, regulates it, slows it down. So that introduces a more typical population to have this kind of population growth pattern. This is what we call a logistic curve, S-shaped curve. Now, the very beginning of that curve is very reminiscent of what type of growth?
Exponential.
Exponential growth. But as the density increases, the growth rate decreases. And what is the growth rate when it flattens out up there? Zero. Did you have a question? It looks like you were raising your hand. Did you have a question? All right. My bad. So this is more like what you see in nature because the reality is the population grows, resources become limited, and there is some set point in which the resource availability in that particular environment can sustain that number of individuals, not more, not less. And we have a name for that number. That's called the carrying capacity of that particular environment for that population. And that'll be a bullet point in a slide or two. Right? So that's a number that can be sustained for a prolonged period of time with the resources available in that particular environment, carrying capacity. So that gets us to a discussion of exponential versus logistic growth. And the difference is that in exponential, the R, that rate R that we multiply n by to tell you how much it's going to grow, never changes, right? So in our model, it's 0.046 for those whooping things. We're going to be 0.046 the next year, 0.046 the following year, regardless of what the population of cranes was. Doesn't change. So R never changes in exponential growth. So R is what you multiply n by, and as n gets bigger and bigger and bigger and bigger, the product of R and n gets even bigger at a faster rate. That's what exponential growth is all about, right? But in reality, and another way of saying that is R is density independent. R does not change as a function of population density. And that's just not realistic in natural populations. So logistic growth takes into account the effects of an increasing population size on the growth rate. And what do you think the effect of an increasing population size will be on the growth rate R? Will it increase it or decrease it? Decrease it. And what will R be when there's no more population growth? 0. So, logistic growth, what we find is R changes as a function of density. The bigger the density, the smaller the R. What kind of a relationship is that? Direct or indirect? Indirect. As one gets bigger, the other gets smaller. That's what we call an indirect relationship. So that's more realistic. That's what's really happening in natural population. So R decreases with increasing population density. So that would be an example of density-dependent growth, where growth is going to be a function of the density. High densities, you get less growth. At low densities, you get greater growth. Now, how do we use what we know about the logistic curve to come up with a mathematical expression that captures this pattern of growth? All right? So how do we take this picture of logistic growth as we grow, where you see population, the incremental increase gets bigger and bigger and bigger every year, right? Because you're growing exponentially. But then as the density starts to increase, R starts getting smaller and smaller and smaller, and so each year you're adding fewer and fewer individuals to the population until you add no net new individuals to the population. And the population asymptotes out to a growth rate of 0, and at that level we call that K, the carrying capacity. Again, C is a very important letter. It stands for cost in ecology, so we use K because C and K are pretty close. We've done this before, right? When did we do this before? In evolution, when do we substitute a K for a C? The KT boundary, Cretaceous, right? I was hoping someone would spell Cretaceous with a K. I did. Good.
I heard that the Germans spell it.
Oh yeah, they took like
We've got different words for almost everything. Every time I understand foreign language.
Because they spoke under the Venezuela.
I guess it's no.
Yeah, but I know what era I'm talking about. Yeah.
Okay.
Oh yeah, you told me.
While we're on the subject of Germans, K's, and how they spell carrying capacity, or Cretaceous, I'm sorry. Let's talk about carrying capacity and flesh it out. Carrying capacity is abbreviated with big K. And what does it represent? It represents the maximum number of individuals that can be sustained for a prolonged period. Sustained means, out into the foreseeable future in a given habitat. It's what that habitat can support. And you might imagine different habitats might have different Ks for the same species. Really, really resource-rich habitats would have a higher K per species than resource-poor habitats, right? And what determines K? Well, it's determined by a bunch of factors. Abiotic and biotic. So abiotic factors like temperature and precipitation and nutrients and habitat area and all these other things, habitat quality, water quality maybe, light levels, all of these things would go into delineating the amount of organisms that can be sustained. But also, there's going to be a bunch of biotic factors, predator density, competitor density, things we're going to be talking about in community ecology that are going to be also utilizing those resources or removing individuals from the population and inhibiting its growth. Okay, so there are a lot of factors that go into determining what K is. It's very complex matrix. So it varies with habitats. Some habitats are good habitats for certain populations, and K would be higher than poor habitats. And that should be intuitively make sense. Another thing about it is, I guess a metaphor you could use would be like employment. Certain regions of the country have better employment opportunities, and you can sustain more paying jobs than others, right? Okay, even though it's the same type of job. So that would be one way to think about it. And the factors that are responsible for that are complex and multiple. All right, so now how do we incorporate what we know about K into an equation that captures this logistic growth? Well, there it is. Boom. Yes. All right. What is that? Well, let's break it down. First of all, a little calculus. Don't want to scare anybody if you haven't had calculus yet. But dNdt just means the change in density as a function of the change in time. It's a rate. Right? How many of you had calculus? All right, so it shouldn't scare you. dNdt shouldn't scare you, right?
No.
Okay. All right, good. Now, if you haven't had calculus and you're scared, let me give you a little oral comment and say, I'm not going to have you do an actual calculation using this equation. Okay? The only calculations you're going to do are the ones we gave you for exponential growth. But I want you to understand the rationale behind this equation. So we say that in logistic growth, the change in number over time is going to be a function of the maximum change possible, the fastest the population could possibly grow if everything was ideal in a perfect world. That's our max, or the intrinsic rate of increase, times the number of individuals, because remember, you start with the number of individuals and they have that growth rate, so you multiply them by that growth rate to give you how much you increase. But then you regulate it by this little expression, K minus N divided by K. That's kind of a fraction that tells you how crowded the population is in terms of resource consumption. Let's think about this. K is a fixed number for a habitat. That's the maximum that can be sustained there. If N is very small, the fraction K minus N divided by K is going to be what? Close to what? Let's say K was 1 and N was 0.01. What would that fraction be? 0.99 divided by 1, or 0.99. So essentially it'd be 1, right? So you wouldn't really be able to tell a difference in the growth rate. Okay? But what happens is that N gets bigger and bigger and bigger. That number K minus N gets smaller and smaller and smaller. And what happens to the number when you divide something that's smaller and smaller and smaller by the same number in the denominator? That number gets smaller and smaller and smaller until N equals K. And when N equals K, what happens? The numerator becomes 0. And 0 divided by anything is
0.
0. So there's no growth. So what this saying is the bigger N gets, the smaller the growth rate gets. Because the more of K you've used up, and the less resources are available to promote growth. So that's what the logistic growth equation is. It's using K as a regulator on growth. So if N is small, R is close to R max, and the population grows exponentially. Population boom, right? But as N increases, the effect of R, this right here, the growth rate of the population decreases, right? Because of the fact that this number is getting smaller, so this number gets smaller, and you're multiplying this by an increasingly smaller number. As N approaches K, R becomes 0. And population growth levels out. It's at carrying capacity. Now, the truth of the matter is, populations never just maintain the same number. But what happens in stable populations, what happens is they go, it's kind of like your thermostat in your house. If you've ever set the heat on your house, be, of course, you would never set it higher than 65 degrees, right? Trying to maintain and minimize your carbon footprint. But it's never actually 65 degrees in your house all the time. It gets a little warmer, and the heater shuts off. And it gets a little colder, and the heater turns on. And the idea is that it turns on and off more rapidly so that the amplitude gets less and less and less so that it basically becomes stable over an average value. And that's kind of what populations do. Very stable populations have slight fluctuations at K. Populations recover may overshoot K wildly, right? And then come back, and then come up, and then come back, and then they sort of gradually attenuate. So it's never actually perfectly constant, but on average, it seems to stay stable. All right, so now when we compare the two forms of growth, we can see what the effect of adding this expression to the equation does to the shape of the curve. This is exponential growth. This is logistic growth. And this dotted line is K. Now that we know that, we can start talking about population growth in the two distinct regions of the logistic curve. What two regions would you identify are distinctly different in the logistic growth curve, this blue curve? Anyone want to venture? How could we break that up into two different regions? The region that seems to have what type of growth? Exponential or density-independent growth, and the region that has highly density-dependent growth. Now, in fact, there is density dependence here, but its effect is minimal. It's not until you hit this point of, what's the word, inflection, that the effects of density become increasingly more pronounced. So we generally refer to this region of the curve as the density-dependent region, and this region of the curve as density-independent, and different factors influence those two different portions of a population's growth curve. So that gets into it. And here's an example, real example of data. Two different species of paramecia grown in culture. There's a fixed amount of resources in that culture bio. They put a few paramecium in, they start doing their reproductive thing, increasing in number, and then they reach somewhat stable levels. You can kind of see how that logistic S-shaped curve is recreated for these two species. But here are two different species, same culture media, different bios, of course, two different caves. Who has the higher cave? Aurelian, right? Who has the lower cave? Baudadin. Use some insight and some intuition and postulate why the green one has a lower cave.
Bigger.
Well, they're basically, green ones are Americans, and the blue ones are just about any other country in the world in terms of individual resource utilization, right? Okay. So you could postulate that green paramecia have a higher resource demand, so fewer can be sustained in the same environment. And that's exactly what the case would be. Okay. All right. So let's talk about these factors limiting population growth. We can break them down into two categories. Factors that are density independent, and their influence on the population's growth don't change as a function of population size. So these tend to be factors that set K, right? Sunshine, precipitation. These factors don't change as a function of population growth. They have the same effect on that habitat at low populations and high populations. They set the potential for that habitat. They're what we call abiotic. They're usually abiotic in nature, but not always. In contrast, we have what we call density-dependent factors, and these are factors that will change as a function of density. They may become more intense as densities increase. These tend to be more biotic interactions. Competition, predation, these kinds of things. So they become more pronounced with increasing density. So there's a clear relationship between them and the population density. And we're going to go through and give you some examples of density-dependent factors. How certain factors change their effect on the population changes as a function of density. So again, what we're talking about is density-independent factors are largely controlling population sizes in this portion of the curve. But density-dependent factors have a bigger effect on population growth in this portion of the curve. So we can refer to this portion of the linear curve as the density-independent curve. And this one really is the more dramatically density-dependent curve. So here are three different examples of density-dependent factors. These are all examples of birds. There's a lot of birds in the study. Birds are nice animals to study in terms of population because they breed in a certain year. You can count how many eggs they produce pretty easily. They sit in a nest, so you can sit remotely and watch with binoculars how many chicks are fledged. You can tag them. No one gets too upset if a few of them, wind up becoming museum specimens, that kind of stuff. So what we have here is on the first panel, a resource thing between males. So you have male density on the bottom axis and the percentage of floaters. How many of them don't have territories on the top axis, right? On the y-axis. And what you see is as the number of males increases, surprise, surprise, the number of males that don't have territories increase, right? Why? Because there are a fixed number of territories in a habitat. And who are going to get those territories? Well, when there are very few males, everyone gets a territory. It's a classic case of musical chairs, right? But as the chair number goes down, or as the number of people playing the game increases, that'd be a spin on musical chairs. Rather than taking a chair out, add another person every time, okay? New player, right?
That's fun.
So, pretty soon you feel the effects of density dependence on your game.
I'm going to do that.
So, once there is more people than chairs, there are going to be someone without chairs. Just like there are going to be birds without chairs. And as that number increases, more and more males will not have a territory. And that has a direct consequence on their ability to attract and get females and have offspring. So that's going to have an effect on their business. Here's another example. Number of breeding females and the percent of young bred per female. So the bottom axis is just the number of breeding females in a population. The y-axis is how many young each female successfully kicks out of the nest. Okay? So that's a measure of her fitness. And what do we see? As the female number goes up, each female, on average, can successfully raise fewer chicks. Now, why do you think that is?
Less resources.
Fewer resources. Your parents will all probably have many, many times told you about how they have to break their back to put food on the table for you and give you clothes and pay for your college, right? Well, just imagine if there were fewer jobs out there or fewer supermarkets or fewer colleges, how much harder it would be to get all their kids, out successfully raised. So that's the idea. With more and more birds trying to raise kids, they're out there rubbing up worms and finding nest sites and everything. It's harder and harder for you to crank out as many kids because there's less pie. I mean, if the pie stays the same, more people are taking slices out. But I like this one best. Here's the number of adults in autumn and the proportion of juveniles surviving the winter. So if you look at how many juveniles survive the winter as a function of how many adults are around the previous fall. And what you see is the number of adults around goes up, the number of juveniles that survive go down. Now, why do you think that is? Because in winter, resources become more scarce. And who gets the resources? The KG veterans. That's the way I like to think of it, okay? KG veterans, right? The ones who have life experience, that are smarter, that know where to find food in a food-poor environment, as opposed to these sort of inexperienced, naive young birds going, where's the food? Where's the food, right? So they don't make it. But if there are fewer adults, there's more resources, and more of them might have survived. So these are all examples of density dependence. Two other, the bottom one is just basically a repeat of the pledging. I think a little earlier, talking about how many eggs you get. But the top one is actually interesting because this is somewhat the faculty member here did with another researcher up in Oregon. This is looking at proportion of fish that survive as a function of density of the fish. And they did this experiment. They created these little micro coral reefs in the Bahamas. So they took coral and they put it in the middle of a great big huge sand plain. So it's this little reef isolated by this vast expanse of sand. And then they took these reefs and they stocked them with these little gobies, right, at different densities. Now, these gobies are eaten by predators. They're eaten by grouper and by pelagic predators like jacks. And so they use the coral to hide from these predators. So it's another case of musical share. The more fish you stack in these reefs, right, the less few of them are going to be able to find a hiding place. So when it's low densities, everyone gets a hiding place. Predation rates are very low. But at high densities, quite a few don't get hiding places, and they get eaten. And the ones that don't get hiding places get eaten. So that's a density-dependent, classic density-dependent factor. And it's driven by predation pressure. Okay. I'm not going to bother with this example because it's basically a disease example where they just look at. But another example of how density-dependent factors work is, and you've all probably experienced this, in a crowded room like this, right? If somebody who is highly infectious with, say, the stomach flu that's been going around, right? What's the chance that someone else is going to pick that up in this room versus a classroom of this size with 8 people in it, all widely dispersed, okay? So at high densities, disease transmission is much higher. And so that would be another example of density dependence. And there's a great example of that in human history from the 1400s. Anyone know what that is? Plague, Black Plague. Where did all people die from the plague? In the cities, right? Not in the country, because it was transmitted by fleas biting people and then transmitting that parasite from person to person to the flea. And so at high densities, people were sharing fleas, I guess, which didn't happen. So this gets us to this notion of R versus K selective species. Now, what do you think these two terms refer to, R versus K? Well, K should be an easy one. Carrying capacity. What about R? The growth rate. That's right. So R selective species, they live in a world influenced and driven and parameterized totally by the growth rate. They don't really care about K because most of them never even get to experience what K is. They never get there. Okay? And then again, thank you, Bill Gates, for capitalizing letters when I don't want them capitalized. Let's get rid of them. So R refers to the intrinsic growth rate. And these species show rapid growth. These populations are always booming. Boom, boom, boom. They're growing rapidly because they're in that lower portion of the curve that's dominated by the influence of R. Okay? And they have other aspects that make them able to do that. They have very good dispersal. They're very opportunistic. They're always sending out seeds, germs, spores, all over the place. And some of them will find a place that's unoccupied and boom, they'll grow. And the population will crowd up. Okay? But they have a short lifespan. Okay? Their strategy is get in there, grow up, have kids, die. Okay? Like by tomorrow. Okay? Because if you go to the day after tomorrow, you're going to be overgrown or eaten. So live fast, play hard, die young, live a good looking life, and lots of babies. That's their strategy. Get it done. Live life in the moment. They're all grasshoppers. They're not ants. Okay? For those of you who know that from soft data. K-selective species have a very different view on the world. We've got time. There's no hurry. Let's wait until we're really ready. Okay? So K refers to carrying capacity, right? And these organisms have very slow growth. They take their time reaching maturity. They live a long time. Now, there are aspects they They take their time because eventually they're going to choke out all the others and take over the place, right? And since they're going to live a long time, they don't have to put a lot of energy into reproduction. They can put a little bit every year, and over their long lifetime, they'll have a lot of reproductive success, right? So they tend to be superior competitors. Whereas our selected species, our selected species tend to be high competitors. And the example we give of them, two plants. One that's R selected, one that's K selected. There's a dandelion. Okay? Dandelion, you wake up one morning, your nice lawn, and there's a dandelion already blooming there, right? Okay? Where the hell did that come from, right? Just started up. That's how quick it grew, right? You wake up the next day, it looks like that with the little fluffy things, all right? It's already reproducing, 2 days old, right? And then your neighbor's kid comes over and picks it up and goes, and all those things fly to all parts of your garden and land, and so they'll sprout up there. Okay. Back inside, there's a shotgun full of rocks. It's got to do that because by the day after tomorrow, some other plant's going to overgrow it and kick it out of that spot. So it's got to take advantage while it can. It's living life hard and fast in the moment. Then you have an oak tree. Those acorns don't fall, the acorn doesn't fall apart from the tree. You ever wonder where that expression came from? It actually came from an oak tree, right? Okay. It falls down, it doesn't disperse much. It relies on animals largely to disperse it. Squirrels and deer and things like that. Okay. It takes a long time for that acorn to grow up in an oak tree. It doesn't produce nearly the same ratio of seeds to biomass that the dandelion does. But it's a superior competitor. It's going to do that. It's a case. Yeah.
Would all good seed dispersal species be R selected species? Most of them. Majority.
All right. That's just I have a table in your book that summarizes some of the aspects of R versus K. You can read that if you want in your book.